Welcome to Chapter 5, Thermochemistry, as we march through the book here. This chapter, it's a tough one. It's got a lot of equations in it that are really physics equations or physical chemistry equations. That course is normally taught the junior year for a chemistry major, so we got some time for that. And a lot of it's not actually on the AP test. You'll see there's a lot of equations in this chapter, and then you look on your AP reference sheet and you're like, well, that one's not there, that one's not there. But a lot of the equations that are on your reference sheet are there because of these. So this is the foundational work. And so I'll try my best to kind of point out of this is what we need to know, or this is, important for this later on. But I'll try to highlight which parts you absolutely need to know for the test, and then which parts are just kind of general knowledge that'll help us out in the future. I also point out that this is the thermochemistry chapter here in chapter 5, but then when we get much later in the course, around chapter 19, all this stuff is going to come back plus some more. So we're going to kind of teach it here in order. This is still a foundational chapter, an introductory chapter, according to the textbook authors. This is all just here's some new stuff of what we do in general chemistry, and then we'll come back to it later of, okay, here's what we can really do with it. So this chapter is all about energy. We said energy is the ability to do work or transfer heat. And so make sure you know that definition. Because if you see work, you see heat, it means we're talking about energy. This is all about thermodynamics, which is about energy and its transformations, right? Or literally, it's the power and motion of heat. But energy and how it moves around, how it changes forms. And so thermochemistry is when we have the chemistry that causes these heat changes, these movements of heat, this transformation of energy. So thermodynamics, thermochemistry, I use them interchangeably sometimes. Technically, thermodynamics is the more general term, and then thermochemistry is when it's because of a chemical process or a physical process of chemicals. That's what we're looking at there. All right, and so this equation here, it's often known as Coulomb's law. It's not labeled as that here because there's a couple different forms of it, but this is an incredibly important equation that comes up on the AP test where they'll say, justify this using Coulomb's law. And you're like, what the heck's that one? What it's about is about electrostatic potential, right? The fact that opposites attract, like charges repel, right? We know opposites attract. Well, that's the general form of Coulomb's law. So what it says is we get some energy of attraction here. It's equal to some constant. Don't worry what it is. It's just constant. Q1 times Q2. These are your charges. So if you have bigger charges, like +3, well, that's going to have more interaction, more energy than a +2 or a +1. So the bigger the charges, the bigger the energy difference there, or the bigger the energy we're talking about. And so Q1, you could say, okay, that's my plus charge. Q2 is my negative charge. Doesn't really matter, but we've got those charges, plug them in. D is the distance between the two charges. So if the charges are very far apart, well, it doesn't matter if they're opposite. They're not going to attract too much, right? If you have two magnets and you're holding them way out here and you let go, nothing happens. But then as the distance gets smaller, then you start to feel the two magnets kind of pull towards each other if you're holding them right. Or if you have north and north, right? They start pushing against each other. Well, that's because this distance is in the denominator. So as the distance gets very small, that makes the whole term get bigger and bigger, right? And so this works whether it's an attraction or a repulsion. It's the same equation. It's just if your two charges are the same charge, if they're both positive or both negative, well, then this will be a positive energy and it's repulsion. As you get closer, the energy goes way up because they don't want to be together. They don't want to be close. They want to push back apart. But if they're opposites, well, then we'll get this drop in energy because opposites attract. Now, officially, if we were to look at the full picture, this one would go to a minimum and then it would go back up for the negative one. And we'll get this in a later, maybe I think it's a later chapter. But that's because, think about atoms have volume. At some point, they get too close together, and now you've got two different things trying to be in the same space and overlap, and they crumple together. It doesn't work. So there is a distance greater than 0 that is the most stable before they end up trying to crash into each other. Right? And then finally here, let's remember joules. the definition for our energy unit, it's a kilogram times meters squared divided by seconds squared. That's what a joule is. And so when we have some other terms in this chapter, they're going to say, oh, we can rearrange this, we can sub this in. And it's always because, oh, we can figure out how this works to get back to joules. All right? But make sure you remember this equation. It's a form of Coulomb's law. It's all about we need bigger charges get us a better energy, and a smaller distance gets us more energy. And then it's just a question of, is it more repulsion or more attraction based on opposites or the same charge. All right, so here we go. Here's our example with the ions. If they're far apart, not a lot of attraction, right? It's a less than 0, but it's not a really good one. Oh, but as they get closer together, now we get lots of attraction to get them in that lineup and stay there. So we see attraction between opposite charged ions, and this is why we get an energy release when we form ionic bonds, because now energy has dropped. Well, it means it's got to be released to the outside because energy is conserved. So you'll always drop in energy and release energy when bonds are formed. You will always go up in energy. You have to pump energy in when you want to break bonds. So if we want to pull these ions back apart, we got to put the energy in to separate them. All right. So that leads us then to our first law of thermodynamics. Energy can be converted from one form to another, but not created or destroyed. You know this is conservation of energy. So you know when we heat our home, if it's like a gas or a oil heater home, then we'll use chemical energy. They'll write it to burn the gas or burn the oil, and then that released energy heats our home. In plants, right, photosynthesis, the sunlight is converted to chemical energy when they absorb that energy. So it's always about we can transform it, but we can't, create or destroy out of nothing. And we have tons of examples of this. We do have to have a couple definitions here about what we're looking at. And so we always use the system versus the surroundings. The system is the specific thing we're looking at. Maybe it's the specific chemical molecules, maybe it's the specific beaker, the specific container, or maybe it's just a portion of a container here. But that's the system. What are we explicitly looking at there? Their surroundings are everything else in the universe. So right here, if they say here the system is the portion of the universe that we single out, well then everything else in the universe, the entire universe, is the surroundings. Now normally we can ignore most of the rest of the universe. You don't see us measuring, well, what happened to that star out there because of this chemical reaction? Because we can focus on, well, the immediate surroundings. But officially, the surroundings are everything else in the universe. All right. With these systems, we have a couple different ways of looking at it. We have an open system where mass and heat can be exchanged. So this would be like if you had a reaction going on in a beaker and maybe gas was formed. Bubbles are coming out. Well, those bubbles fly out into the air. So mass is going out of the beaker. That's an open system. Or maybe you have something where a chemical gets dripped into the beaker over time. Well, then mass is being added over time. That's an open system. A closed system is usually what we prefer for our careful measurements. This is where we can exchange heat, but not mass. So this is where we have maybe two aqueous solutions mixed together in a beaker or some other container, and while they're going to maybe release heat and heat up, and the beaker heats up, or maybe they absorb heat and the beaker gets cold, but they stay in the beaker. All the chemicals stay in the beaker. That's a closed system. If you have gases, then it's got to be something like this thing here, where it's a sealed container. Maybe it's got a movable piston, maybe it's a balloon, maybe it's a sealed tank, but the gas can't come in or out. That's how you have a closed system with gases. Got to seal them in. So heat can be exchanged, but not mass. All the chemicals have to stay in. No extra chemicals can come in. And then number 3, the third type of system that we would love to have is an isolated system, where heat can't be exchanged, mass can't be exchanged. All the heat stays in, all the mass stays in. Nothing gets added, nothing gets lost. But it's really hard to isolate systems from the rest of the universe. It's basically impossible. This is one of the reasons we can't get to absolute zero, because there's always some connection that's not letting the system be isolated. And so just, we have to watch out for that. but we try to get close. So when we have insulated containers like a thermos, right? Or in this unit, we'll talk about coffee cup calorimetry, where we'll use multiple styrofoam cups because then the heat mostly stays in. None of it, not too much gets out through the styrofoam. That's not completely isolated, but it's getting closer. So we try to do our best with the materials and the budget that we have available. All right. Internal energy. This is all the kinetic energy, all the potential energy for everything in the system. So if you're looking at a molecule, it's all the energies of the atoms and all the electrons flying around the nuclei and vibrations as the atoms move a little bit, as the molecule twists and turns. All of that together is considered internal energy. That's the letter E that we use. But we can't know it. It's basically impossible to know it. There's a few rare cases that I'm not going to get into because I honestly don't remember them. We just can't get E very easily. But we can get the change in E. We can get delta E. We can say we don't know what it was at this time, and we don't know exactly what it is this time, but we do know the difference before and after, and that's what we can get. So we go for delta E. So by definition, delta E is the final energy minus the initial energy. And this is going to go for pretty much every delta we have. Delta T, delta H, delta whatever. It's always final minus initial. So make sure you know that one. That will be extremely important on the AP test and every test you take in chemistry. Whenever you see a delta something, it's final minus initial. So if we look here at this state here, if the delta E is greater than 0, that means our final energy was greater than initial. The system must have absorbed energy from the surroundings. Energy was taken in to raise the energy. So that's this picture here in blue. If you have the initial state, if it goes up in energy, it will be a positive delta E. If, on the other hand, delta E is less than 0, that's when the final was less than the initial, and energy had to be released to the surroundings. So that's this picture here in red. We start at some initial amount, and we drop in energy to our final. That's a negative delta E. Energy got released. All right, so that's the same in Chem 2 we talked about for thermo. Hopefully you got that part and remembered it. Negative energy means heat was released, or in this case, energy was released, not necessarily heat. And a positive delta E, energy was taken in, absorbed. All right. Well, whenever we talk about these energies or other thermodynamic terms, we always have to have 3 parts to them. We have a number value, that's our magnitude. We have a unit, that's where we might space the magnitude. Maybe we use joules, maybe we use kilojoules. Maybe for some reason we're using calories again, but we're using our the unit to tell us how much of a given unit. And then we always have a sign. In thermo, it is very common that even if it's a positive number, you still put the plus sign in front so that you're being explicit to the reader. This was a positive energy, so they know, okay, energy was absorbed, right? Because that's what the positive delta E means. So it's really important. Obviously, you got to have the negative number if it belongs there, but we also often usually put the plus sign for a positive energy or some other term. And so again, positive delta E, the system gained energy. Negative delta E, the system lost energy. All right, so let's talk about, well, how can we change this energy? What can make energy change? And so there's 2 ways. We've got heat, which we use the symbol Q for. I can't tell you why, just heat is Q. Remember that. And work is W. That one, I'm going to assume it's because work starts with the letter W. But yeah, I have no idea why heat is Q. It just is. It might be because whoever was figuring this out in the first case might have been speaking a different language, and in which case Q might make more sense there. And so we have this equation that because the energy is dependent on the heat and the work, the delta E is equal to Q plus W. The change in energy is equal to the heat and the work that was done either on the system or by the system. And so we see here, okay, say the system is the inside of this safe. If heat is gained, or if work is done on the system, well, then there's more stuff going into the safe, so the internal energy gets bigger, and delta E is positive. If, on the other stuff, energy comes out in the form of heat, or if work is done by the system, and we'll get into both these things in a little bit here, so that means stuff is coming out of the safe, Well, there we have a negative delta E. Right? So let's go ahead and talk about, well, how do we know which one is which? For Q, for heat, a positive Q means heat is gained. A negative Q means heat was lost by the system. So this is going to be very similar to some stuff we did in Chem 2 with, if you remember, delta H and enthalpy. We'll find out in a few slides here or in a different video that Q and delta H are very, very related. But same thing. If it's positive, you're gaining heat energy. If it's negative, you lost heat energy from the system. W, it's a little bit different. A positive W means work was done on the system, right? And then if it's a negative, that means work was done by the system. So we'll get to work in a few slides. Well, what does this mean, on or by? We'll get to that. But same thing here. Positive means energy was going into the system. Negative means energy was going out from the system. So you kind of think, well, if you do work, if you're the one doing work, then you're expending energy. You're releasing energy to do it. That's why it's negative here. So then for E, or delta E, this should be, if you have an overall positive, so maybe one's positive and one's negative when you combine these things. If it's overall positive, you've gained energy. If it's overall negative for delta E, you have a net loss in energy. Okay, so when we talk about heat, so now let's focus on Q a little bit. When heat is absorbed, we call it endothermic. We should remember from Chem 2. So here's a very common experiment. We take some ammonium thiocyanate with some barium hydroxide, and you just mix them together. Don't even need water. Just mix them together. They start out at 23 degrees Celsius, and after they mix them and they react and they form barium thiocyanate, ammonia, and a bunch of water, it's endothermic. That temperature becomes negative 11 Celsius. And a common demo is to put this beaker on a piece of wood and then put a small squirt of water between the two, because when it gets down to negative 11 Celsius, it freezes the water, and then you can pick up the beaker and it picks up the wood block with it. We're not allowed to do this demo in school because barium can be toxic to your nervous system, so you'll just have to take my word for it until I find a video of it. But that is endothermic. It's absorbing heat from the surroundings. Here, it absorbed it from the air, and that's why the stuff left in the beaker got colder. It was absorbing it, from the stuff in the beaker that wasn't the system. And if we release heat, that's what we call exothermic. So here they're putting some potassium in water. That creates potassium hydroxide and hydrogen. They added some phenolphthalein in there, so the hydroxide would turn it pink. You don't really need that because, there's sparks. It's flying. You can see, there's definitely heat being released there when fiery sparks are getting kicked out everywhere. If they measured the temperature, this would get pretty hot. So it's exothermic. So make sure you know those two terms as well. A positive Q, where it's absorbing heat, endothermic. A negative Q, where it's releasing heat, exothermic. All right. This part, little bit different. It still ties in with Q and W and E, but it's like, okay, well, here's some new definitions and then how it applies to those three things. So it says, usually we have no way of knowing the internal energy. It's just, we can't do it. We can't calculate the kinetic energy of every electron and add them all up. It's just not going to happen. But we do know that this internal energy is independent of the path by which we achieve it. Meaning, here's water at 25 Celsius. If it's at 25 Celsius, it has a certain amount of energy. We don't know how much energy, but it's a certain amount. And it turns out it does not matter if we start it with 50 grams of ice and let it warm up to room temperature, or if we start with 50 grams of nearly boiling water and let it cool down to that temperature. This beaker of water at 25 Celsius will have the same internal energy no matter which way we got there. I mean, we could even take this water, heat it almost all the way up to boiling, and then let it cool down. And the beaker at 25 will still have the same amount of internal energy. That's what we mean by it's independent of the path. Doesn't matter how we got there, just that we got there. All right? So that internal energy, because it does not depend on how we got there, we call that a state function. So any term, and we'll get a few more in this unit, anything that doesn't matter how we got there is also a state function. It depends only on the present state, not how you got there. Right? And so delta E depends only on the initial and the final, right? So this one, going from hot water to the 25, is going to have a certain delta E. The one going from ice to there is going to have a different delta E, right? But this E is the same. This E is the same. However we got to the 100-degree water, doesn't matter. This has a certain amount of energy. The ice has a certain amount of energy. But the delta, that is what we can measure because those are state functions. Right? Now Q and W, the heat and the work, they are not state functions. They are not always the same number no matter how we got there. So they give us this example of a battery. Maybe we put it in, they say short out, but say there's like an old light bulb, an incandescent light bulb, where when energy goes through the coil, it releases light and heat. Well, when it does that, that's all Q, right? So that's this picture here. It's all released as heat. Okay, it's a change in energy, but it's just all heat. Oh, but what if we put that battery in a fan, right? And here they even put the nice buttons there, right? Low, medium, high, and then oscillate on and off or whatever. There's the plug in the back for it, right? But the fan goes back and forth. It's still releasing heat, right? That's why if you feel the back of it, you can sometimes feel some warmth coming off the motor, right? The motor heats up. But it's also doing work to spin those blades. And so we see, it's now some heat, but also some work. Well, if it's the same battery, say it's a D cell battery, it has the same amount of energy inside it. And so when you start with a completely new battery and completely empty it out, it will still be the same delta E. The battery will still lose the same amount of energy. It just did it by two different paths. One released it completely as heat. One released it as heat and work. So Q and W, right? You can see here, Q, it's a large Q here, it's a small Q there. Not the same value because it depended on the path. Here, work is a decent value. Here, there's no work. Work is 0. They're different values because they're not state functions. Here, it does depend on how we got there. All right, so let's talk a little bit more about work. Heat, we're usually pretty good on. It's okay, yeah, it's either released heat or absorbed heat. Work is a little bit different. So when we talk about work in chemistry, it's the work done by a chemical or physical change. It's the mechanical work associated with a change in volume of gas. Right? When we do liquids and solids and aqueous, usually the volume, it doesn't change very much at all. Even if you change the temperature, it might get slightly expanded or slightly contracted as you heat it up or cool it down. But it's so slight, we can basically ignore it. But with gases, right? Gases expand. They fill containers. They definitely change volumes. So for that, if a gas is formed or if a gas goes away, we've got to talk about it. So if we look at this picture here, we have some initial state where there's gas here at the bottom. There's atmospheric pressure pushing down on it. Excuse me. Something happens and the volume goes up. Now the piston gets pushed way up here. The air pressure is still pushing down against it, but we've got this change in height, which gives us a change in volume. And so a change in volume, pushing against the pressure, it turns out that that's energy. All right? So this will be our last slide for this video. It says we can measure the work done by the gas if it's done in a vessel that's been fitted with a piston, because according to our rules, work is equal to negative pressure times the change in volume. So negative P times delta V. The work is negative. We have to put that sign in there because work is done by the system. If our reaction is pushing against the air pressure, if it's pushing that piston to expand, well then that's releasing energy, so it has to be a negative value. So that's where that negative is coming from, because volume must be getting bigger, pressure stays constant, so we have to have a negative there so that it lines up with what we expect. So we'd say, okay, we have some air pressure, we'd measure that, we would measure the change in volume, we'd plug it in, and when we do this equation, we get it. For this one, the reason it works, remember, volume is just like maybe meters cubed if we're using SI units. Pressure is force divided by an area, right? Well, that means then, oh wait, volume is like area times a distance. And so if we do pressure times a volume, the areas cross out, and now suddenly we have a force times a distance. Well, force times a distance, that's energy, right? That's physics energy. If you took AP Physics or taking it now, a force across a distance, that's what we would use to get that. So it would be kilograms per times meters squared per second squared. So that's how this works out. Even though it's like pressure and volume, how's that energy? The units do work out to get back to our units for joule. All right, so just keep in mind that's an important equation. That work is negative P times delta V. It will come up. All right, we're going to pause there because this, like I said, this chapter takes a while, so we're going to try to chunk it a bit better. But come back in a day or two for part 2. We'll talk more about enthalpy.